Recording.
So, hi everyone, and welcome to this video on the simple Bayesian linear regression. And this builds up on our concepts on basic Bayesian statistics and sort of taking that to the next frontier, which is actually using these concepts to perform a linear regression. Okay, so this is an overview of what we'll do. Let's begin with a quick recap on the Bayesian statistics we've discussed in the past meetings. So, as we mentioned, there's this sort of debate on difference between the frequentist approach and the Bayesian approach. Well, as we know and discussed, in the classical or the frequentist approach, we typically estimate parameters that are fixed unknowns. So, for example, when we typically run a regression, the beta parameter is a fixed parameter and it's unknown. That's why we're estimating for it. However, when we utilize the Bayesian approach into statistics, we treat the parameters typically as random variables. And because it's a random variable, it will have its own distribution, right? And the Bayesian approach, of course, is centered around this Bayes theorem, right? This theorem that Bayes initially sort of came up with. And in the context of our parameter, an unknown parameter, say theta, given the data, we know that the theta, given the data, the probability of that would be equal to the probability of the data given theta times the probability of theta divided by the probability of the data, right? And in basic statistics, we found out that this here was the posterior, okay? This here is the likelihood function. This here is the prior. And here is some normalizing constant at the bottom, right? So effectively, because the normalizing constant is not a function of theta, we can omit it in our analysis, right? We can just normalize it, and instead of using an equality, we will be using a proportional to sort of constraint. Okay. So just to recall the typical linear regression, okay, we know that in a standard linear regression, we typically model y, some dependent variable, against some independent variables x, right? And we typically come up with the notion that y is equal to x beta plus epsilon, epsilon being an error term. And that error term follows a specific distribution. In particular, the distribution has a mean of 0 and has a variance of sigma squared I, right? Has a constant variance, right? To adhere to the homoscedasticity assumption. Now, one way for us to estimate a linear regression is through the method of least squares, or OLS. And that method basically uses the minimization of the residual sum of squares. So the criterion by which it's going to try to estimate this beta is that it's going to try to search for the beta that will minimize the sum of squares, right, of the residuals. And we find that our typical formula being x transpose x inverse x transpose y, our standard OLS formula. Now, of course, in the frequentist sense, we've discussed the limitations of this OLS, right? For the first is that it will only give you one point estimate, right? It only provides a point estimate. It doesn't provide a distribution, but rather a single answer, a single number, right? The second is the uncertainty quantification is quite limited, right? Quite limited to the having errors and confidence bands around it. And the last, which we sort of discussed and alluded to, is that this estimate doesn't really incorporate prior knowledge. All you need to come up with the estimate is the data itself, right? But if you had some prior understanding of the relationship between y and x, right? Perhaps that may be helpful in understanding what the true value of beta would be, right? That's subjective, whether or not that's a subjective value or a positive value, okay? That's up to you, right? So let's now discuss how this Bayesian sort of methodology works under the linear regression. So it starts like this. Okay, we start with exactly the same model, right? we have y is equal to x beta plus epsilon, with that epsilon having a distribution. Then our key parameters to estimate are the following, right? We would want to understand what are the regression coefficients beta, but in keeping, we also want to understand what the error variance is, right? What the error variance is, right? And the goal of finding these unknown parameters is essentially trying to find the posterior distributions of these two parameters, given the data and other parameters. So our goal is to find the posterior distribution of beta, conditional on the data and on the error variance, as well as what is the posterior distribution of the error variance, conditional on the data, right? And the process by which we do this, okay, involves our typical Bayesian methodology. It starts by introducing a prior. We need to define prior distributions for parameters. And in doing so, define hyperparameters that will govern the prior distribution as well. The second involves the calculation of a likelihood function from the data, right, which we know about. And we know that the product of a prior and a likelihood is proportional to the distribution. And that allows us to derive the posterior distributions of the data, right? And lastly, we will sample from this posterior for inference. Right? So that's sort of the general four-step procedure that we're going to do to be able to estimate this framework. Right? So let's get into the math. Okay? In our model, we have a likelihood function that looks something like this. The probability of y, which is our data, okay, things we're interested in, given our unknown parameters, theta, which in this case is beta, and the error variance, is proportional to this term here, right? This term over here. And as we noted, this is just basically a very similar sum of squares minimization. Okay, it looks very similar to a typical minimization for sum of squares. Next, in order to be able to operationalize this, of course, we would need priors, right? We would need prior distributions. And our prior for beta follows, okay, is proportional to this distribution over here, right? This term here. And our prior for the error variance looks something along these lines, right? Typically following an inverse gamma distribution, okay? And as I noted, right, to derive the posterior distributions, well, all you need to do really is to multiply it with the likelihood, right? So multiplying those things with the likelihood will give you these things. And what you'll notice is that the posteriors will now be functions of both the new data coming in as well as the prior information that you've had, right? It's going to be some convex combination of the two, okay? Now let's dig in deeper with the prior and the posterior distributions, right? Our prior for beta follows a normal distribution in this example, right? That distribution will have a mean vector, mu naught, and a covariance matrix given as sigma squared v naught, right? So it's pinned down by two hyperparameters, our mean and our covariance matrix. Our prior for the error variance, on the other hand, will follow an inverse gamma distribution. Okay? And that prior is pinned down by two hyperparameters, which are our shape parameter A0 and our scale parameter B0. Okay? And in keeping to be able to derive those parameters, right, from the posterior, we can get moments from the posterior, and that allows us to derive the mean of the posterior for beta, which is equal to this term, which again is a function of a prior mean and the new data coming in, right, here. The covariance follows a similar story, right? And our posterior for the error variance follows the same. It's a function of prior information, the hyperparameters we've had, and new data coming in, and new data coming in. So that's what we have for the priors, and those are the posteriors. Okay. Lastly, to be able to do inference, we need to sample from the posterior distributions. Why do we need to sample from the posterior distributions? Well, it provides an empirical approximation of these posterior distributions, right? And it will allow us to do one very important task, which is inference, right? It enables also for us to check various properties of the posterior, such as generating a posterior odds ratio and other applications, right? So how do we sample from the posterior? Very simple. In our context, the first step is we want to draw samples from P given sigma squared, okay, conditional on Y. That's from the inverse gamma distribution, which we specified that the prior for the error variance will follow. Then after that, for each sigma squared sample, right, we're going to draw corresponding betas from this probability of B given Y and sigma squared. This is exactly the same procedure as we did in the past, wherein we sampled from the marginal and then sampled from the conditional, right, to be able to derive the joint, right? And we're going to use these samples to calculate statistics and visualize the ending posterior distribution, right? So how do we do this inside of MATLAB? Okay. The code is quite simple, okay? The code works as follows. The first is we're going to initialize the workspace and to load the data. The second is we're going to define prior hyperparameters. I'll discuss what these are about. The third is we're going to calculate some statistics. And the fourth is going to compute, okay, the posterior distributions, which we're all interested in. After that, we're going to sample from these distributions. And last, we're going to plot. So it goes a little bit like this. We're going to load the data set. Then we're going to impose the following prior hyperparameters. These are the parameters that will govern the prior. And these are exactly, okay, from this slide here, right? So we're basically going to define what these are, okay, inside of MATLAB, right? That's what we're going to do. And it follows as here. Okay, we're gonna specify that the mean vector is gonna be 0. Okay, this variance matrix is just gonna be this. Okay, and we're gonna set the shape and scale parameter of the inverse gamma distribution of our prior to have values of 2, 2, right? Same as last meeting. Okay. After that, okay, so again, that's what we're gonna do. We're gonna load the data set. We're gonna set a prior mean to be 0, a prior covariance to be a diagonal matrix. That's an identity matrix. And we're gonna set the inverse gamma hyperparameters to be equal to 2. Okay. After which, we're gonna generate some statistics. Again, these are typical forms that appear in our posterior, right? So we have X transpose X and X transpose Y. So I'm just giving shorthand notation for the two of them, right? Because we're gonna end up computing it from the data. Then I'm gonna generate this matrix, which I also use, which is gonna be a function of the data, right? Using this, as well as this, right? And now these are the things that will govern, okay, my posterior. So again, this is going to be equal to the prior plus new data coming in. This will compute for the residuals, okay? And this will compute for everything else. And those are the sufficient statistics, right? It will compute the sample size and the matrix products for efficiency purposes, pre-allocate them. Then it calculates the posterior covariance matrix and the mean vector for beta. And it will compute the posterior shape and scale parameters for the error variance. Okay. Then we're basically now going to the sampling this part. Okay, we're going to draw 5,000 samples. Okay, and the samples for our error variance will come from this from this gamma inverse gamma distribution. Okay, spin down by these two posterior parameters, right? And we have our beta samples here, okay? And we're gonna sample our beta from this multivariate random distribution. pinned down by the things we've had. Okay? And the last step is going to plot them, right? So we will get the following results as follows. So if we plot this all in MATLAB, we should see here, right? So this is the posterior of our estimate for the model intercept, right? For beta 0, right? This is our estimate for the posterior of beta 1. And this is our estimate for the posterior of our error variance over here, right? So what do these things mean? So these things basically show the central tendency and uncertainty of each of the three parameters that we've discussed, right? And we can see here, okay, credibly, okay, these calculations for the point estimates. You can take a median posterior response of each of them and you'll be able to get that. And drawing from that allows us to get these certain things. Now, let me conclude with the following. What are the advantages of the approach that we had just conducted? The first is that it allows for full uncertainty quantification because we can calculate the whole distribution. We don't just calculate the point estimates. We have a natural framework for having a prediction for the relative uncertainty behind the parameter. The second is that we can use our prior knowledge, right? We can use our domain of expertise to be able to inform our analysis and potentially lead to an answer much quicker, right? And the regularization via priors for small data sets is particularly winning. And the last is a great deal of flexibility, right? So we can typically utilize a hierarchical modeling to basically model very complex things, as well as the framework being very easily extendable for non-standard error distributions. Okay? And there are many applications for this outside of the Bayesian linear regression. The most common one would be for time series forecasting. So that's it for today. Thank you for your attention, and I'll see you in the next meeting. Thank you very much.